Hello, everybody. I know there's some folks still getting snacks, but I will start by introducing our speaker for today. It's my pleasure to introduce James Doan, who is a member of M-Cubed. So James obtained his PhD in meteorology from the University of Reading in 2003, and his PhD thesis was on predictability of mesoscale convective systems. But James shared with me that there were only 3 MCSs over the UK during his PhD time. So he made the good decision to come to the US to experience some, quote, real weather. So we're so happy you did, James. He started as a postdoc in M-Cubed in 2004 and has been a member of the lab ever since then. He is now section head of the Weather Extremes Across Scales group, or WEX, and he studies the behavior and drivers of hazardous weather across scales, and much of his work is in partnership with the insurance industry. And we're going to hear more about that today. So welcome, James.
Great. Well, thanks, Gretchen, and thanks, everyone, for being here and watching online. I'm glad of the opportunity to present some thoughts I have about collective behavior of hazardous weather and the work I've done on that in partnership with the risk management sector. So I'm going to start with this image here. So this is a starling murmuration. Some of you have probably seen these or familiar with them. So the analogy here is that each bird is a hazardous weather event. So there's a whole collection of events, but you can see there's large-scale structure across this collection of events in space and time. And so what I'm talking about today is what controls these large-scale influences on collections of weather events. And let me start by also defining risk management. So here I'm talking about weather and climate risk management, and specifically in the private sector, because that's where a lot of my experience has been, and specifically using the risk transfer tool of insurance. So that's the scope of today. Okay, so why are we all sat here? So 3 goals today. We're going to explore the use and potential use of our science in risk management. So I'm going to present an overview of some interview work I led. And then we're going to dig into some of the physical science that might explain the collective behavior we see in the world. And then I'm going to end with a brief forward look into NCAR's role as a driving force behind the fundamental science that is also used in risk management. So 3 goals. I wanted to start with a thank you slide. So firstly, thanks to the section here in M-Cubed, the Weather Extremes Across Scales. So all these people listed here. These asterisks is to remind me to special thanks to Minga for a lot of the technical work behind a lot of the work I'll present today. And also thanks to Daniel Swain, our research partner, our section's research partner from the University of California system, for some of the inspiration behind today's comments. Now, of course, I can't do this work in isolation, so I work closely with several insurance industry partners. So this has been a really nice career-spanning partnership. So I've been working with WTW, a risk consultancy, since 2007 now, so 17 years. I've worked with Insurance Australia Group since 2015, so that's getting on 11 years now. And then more recently, I started partnerships with AXA XL and QBE. And thanks also to Willie Akami, an industry advisor from the private environmental risk industry. I also want to acknowledge support internally from the M-Cubed Strategic Research Fund for the interview work, and also shout out to Kate Fussell, who I've been working with to strategize NCAR's role in this space. Thanks also to NCAR Directorate Funding for some seed work to translate CESM data into something usable. And also thanks to the Convergent Science Program. So this has been a great experience to allow me to understand how to be effective doing integrated science. And a final thanks to the Mesoclip group, who generated high-resolution CESM results, and the Tropical Cyclone Tracking by Dan Fu and Ping Chang at TAMU. So let's get into it. So how bad can the weather get this year? So how bad can the weather get this year? That's not a question you generally hear in the halls of NCAR. But it's a question at the forefront of the mind of many risk managers. So let's think about this a bit more. So I love this graphic that was recently posted on Blue Sky by Steve Bowen at Gallagher Re. So here's the SPC storm reports from that 7-day episode a couple of weeks ago. So you'll be familiar with this. But was this the most likely outcome? Or was it like in the 10th percentile of possibilities? Is this the 90th percentile of possibilities for those 7 days? I'm not sure we know. And I really like this kind of question because it provides a new lens on our science. And it inspires us to think of physical science questions that we don't normally think about. So we're asking questions about relationships and scalings and maximum probable outcomes, or maximum possible outcomes, I should say, and what drives that range of possibilities. I also like this question because of the word bad. So that's the inherently value-based subjective word. And so if we want to understand what bad is, it demands integration of expertise and perspectives from scientists and risk practitioners and how they relate to each other. Also, to be a bit provocative here, I don't think our scientific programs are directly targeting this kind of question. So this question, or lots of the work we do at NCAR, is driven or is motivated by a desire for better prediction on any timescale. But here we're less interested in predicting the most likely outcome, but more interested in predicting more of the higher percentile outcomes. And also, I think we can reframe it. We can be a bit looser about prediction. It's more about characterization of climatology also. So more on that. Okay, so now I've introduced the flavor of what we're going to talk about. Let's think about the use and potential use of our science in risk management. So I'm going to give you an overview of the ecosystem of risk transfer in the private sector. So I learned from Morris's seminar last week, this is not the overview, it's my view. So I don't attest to the completeness or accuracy, but the idea is to give you a flavor. So here we all are. We've probably got some assets that are exposed to weather and climate, so we hold some risk. We probably can't afford it, and so we pay an insurance company to buy our risk. But now the insurance company holds that risk, and you can imagine an insurance company in Miami, and the hurricane comes along, it also can't afford to hold that amount of risk. So it too transfers it to a reinsurance company, and these reinsurers are global, so they can survive a hurricane hit to Miami. So it's a global system. And then in between the two, there are reinsurance brokers who have also have deep, maybe alternative views of the risk landscape, and they broker deals between insurers and reinsurers. And then we have catastrophe models. So these models quantify risk. More on that in a minute. And they inform a lot of these transfer decisions. And then we have regulators whose goal is to ensure the whole system is stable. So where does our science come in? Well, everywhere. So in my career, I've worked with all of these actors in this ecosystem. They're all interested in process-based understanding of the hazard, as they use the word hazard a lot. And this isn't just passively, them reading our papers. It's a two-way partnership. So in the true word of partnership, where my/NCAR science has benefited from these interactions because it allows me to ask new questions about the Earth system. Okay, so let's think about where the similarities are between our science and risk management. So some key risk management concerns. So for insurance anyway, they're primarily interested in the average annual loss to set the insurance premiums. They're also interested in the maximum probable annual loss for capital requirements. They're also keen model developers. They take observations of losses, and they interact the two. They're very interested in defensible science because they have to defend their decisions to regulators. They're concerned about leadership and position in the market. And they're very concerned about educating their clients to understand the transfer mechanisms that are offered to them. So let's think on the other side what our concerns are, and I don't need to tell you all what your concerns are, but you can see there's lots of similarities here. So we have shared goals, and I think this is the opportunity here. So we're very good at advancing process-based understanding of the Earth system. The opportunity is to connect that with understanding losses. And this is two-way as well, because if we understand how the Earth system relates to losses, we can then dig deeper into the fundamental physical processes that are relevant to loss. So this is the opportunity that we work in. Now, Abby and I conducted an interview study to really get to the bottom of why the industry is not using our science as much as we think they should. And we wanted to give them time to express their frustrations with what we do so we can knit and become more effective partners. So we interviewed 10 experts from that range of actors in that ecosystem I showed. Nice balance in different dimensions. Yeah, so what did we find? Well, firstly, we found that, and I kind of knew this anyway, but it was good to affirm that catastrophe models are the language of risk management. So if we wanted to introduce any new science, new understanding, users have to understand how it relates to what is being produced from a catastrophe model. So I could give a whole seminar on cat models, but in 1 minute, very briefly, they have a weather event set. So this is a collection of, say, tens of thousands of tornadoes. And then they have an exposure, so this is what they insure, say a collection of residential properties. And then they know how these properties respond to the tornado winds, that's the vulnerability piece. And so they run tens of thousands of iterations, and it spits out this loss likelihood curve. So the annual likelihood of a loss within a 12-month period. So just like our global climate models, these have been decades in the making. They're highly successful at what they do at integrating hazard, exposure, and vulnerability. So that's not something we do. And they're baked into all the many of the decision-making processes. They're often regulated to use them, and they set market expectations. So anything we do has to speak this language. All right, so what are risk managers interested in? Well, certainly for insurance, they're universally interested in the next 12 months. And at a very distant second, they're interested in anything on longer time scales. And so that's for long-term planning, but this is for insurance premiums and all that risk transfer I was talking about. This does not mean they're not interested in climate change, because they recognize that the next 12 months is going to sample from the underlying system. It's not going to sample from the historical record. And they're interested in frequency and intensity of weather events. So they can't use, for example, maps of the 99th percentile wind speed across the US, as we typically see in IPCC reports. They need trackable features that they can run over their exposure. So that's the format. So, and less interested about mean events, more about the extremes. And ideally, they'd like it global and consistent. So, that's what we do with our GCMs. They're global and consistent. Okay, this is where it's time for some humility. So I think we'll all agree we're very accomplished at passing peer review. We're less accomplished at passing fit for use. And these two are not the same thing. So let's think, what's the criteria of fit for use? And this is what we heard in the interviews. It's rigorous uncertainty. So studies that just study one aspect of uncertainty are not very usable. I like this quote from one interviewee, what did I just read? So it's very hard for them to figure out if any of our papers are an incremental advance or some major groundbreaking new truth that they should listen to. We're very poor at understanding why our science matters. That's what they tell us. They'd also like to see value-added derived products. So if we're creating a data set of hurricanes, they'd like us just to add the land mask, for example, so they know which data are actually going over land, for example. So really simple things that make the leap from unusable to usable. And delivered by a trusted source. So that's us, fortunately. So universally, NCAR is trusted, along with NOAA and NASA. So that was good. So in terms of the weather phenomena they're interested, it used to be all about tropical cyclones. But recent years, in the past 3 years, the losses from severe convective storms have got to the same level as hurricane losses. So I'm talking about tornadoes, large hail, straight line winds. Flood is insured by the federal government for the time being. So severe convective storms is probably the of greatest interest at the moment, and also wildfire, and not just any wildfire, but the wind-driven wildfire. As we well know, these are the wildfire that drive the highest losses. And so, as I mentioned earlier, they're interested in underlying trends in all these phenomena. They don't want to go through the pain of having to experience increased losses to know there's a trend. They want to come to us so we can tell them there's a trend, and so they can take action to prevent those additional losses. Okay, so they had some recommendations for us, so buckle up. So they would rather we work with them first to identify the science questions. And they want a space to just talk it out, an informal and structured time just to hash out what we know, what they know, to come to identify the overlaps of interest. They also commented that there's an imbalance in the level of interest. So they're very interested in our science. They don't see much reciprocity coming from our side. So I mentioned this small amount, additional analysis. I'm going to come back to this point. So almost universally, they thought fundamental insights in how the world works are a lot more usable than specific data sets. So I'm going to end on that point. And they were rather alarmed at how siloed we are. So they would like to see a lot more academic research into impacts. So that would be us extending our science to the world of impacts. And finally, they'd like us to see or be more engaged in science communication. Because at the moment, you've probably heard, talking to friends and family, they're all complaining about premiums going up, and so the insurance companies are seen as the bad guy, even though those increases are proportionate to the risk. So engagement in trends and weather phenomena would bring everyone up to speed. All right, let's see. So that was a summary of how our science is usable and potentially usable, and then just a couple of slides to show that there's a lot of momentum in this area. So there's this President's Council Science and Technology report in April 2023, and basically one of the recommendations of that report was a need for public weather risk information that's trusted, verified, transparent, and free. And then we had a follow-up conversation at the White House. So thanks to these two for inviting me along. So this was a climate risk roundtable in September of 23, where we basically affirmed the need for this global, free, verified risk information. So you'll notice I had a different colored badge to Everett. That's because I was a foreigner and had to be escorted. Rather awkward, but I got through it. Oh, and my final point is there's a lot of momentum in the crossover between private sector and academia. So some of that efforts I've led. I frequently give talks at the Professional Association of the Insurance Industry, the Reinsurance Association of America, where I talk about the role of process-based understanding. And I've written about process-based understanding for developers of catastrophe models. And then we have this really nice series of books on hurricane risk, authored by academics and private sector authors. I wanted to flag this special issue we have at the moment in Environmental Research Climate on introducing trends into CAT models. And there's a really nice paper by Andrew Gettleman, Claudia Tibaldi, and Ruby Lung on climate nowcasting that I recommend you check out. And then finally, we've had integrated sessions at AGU with industry about connecting climate models and cat models. Some really interesting work going on in this space. All right, well, that was an overview of what we understand about how usable our science, with a bit of social science there. Now moving on to a physical science section. So this is new exploratory work I did into the collective behavior of hazards. But wait, there's one more slide of context. So this is relevant. So before I describe what you're looking at here, the point of this slide is to explain that the tail event losses, so the rarest, biggest magnitude losses, are more sensitive to variability in the hazard than they are to changes of the mean hazard. So my colleagues at WTW, Cameron Rari and Jessica Boyd, did this sensitivity study with a cat model, where they took their collection of hurricanes, so remember it's like 10,000 years of hurricanes, and they added 20% more Cat 4s and Cat 5s. And they added it in two ways. The first way was they just randomly seeded all their 10,000 years with these new hurricanes. And then the second way was they only added the extra hurricanes to the most active years. And so if you think about it, the first way is increasing the mean numbers of hurricanes. The second way is increasing the variability of the annual numbers. And the bars here is the increase in losses from increasing the mean in the gray bars and increasing the variability in the purple bars as a function of rarity of the loss. So these are the big loss years at the end. And you can see the big loss years are a lot more sensitive to changes in variability than the mean. So this is nice.
James, could you say a little bit more about, I mean, it just seems to me that shifting a distribution, its mean, and expanding its variance, in some sense have similar effects on the tails. So this seems like a special definition of variability.
Yeah, so there's two effects, which I'll demonstrate in some physical data in a few slides. If you increase the mean, you're increasing the likelihood of a tail event, and if you increase the variability, you're also increasing the event. So they're both raising the tail. This is the percent increase in losses. So they're both changing the tail, but just the increase of the variability the contribution of both is higher than just changing the mean, I guess, is what this slide is saying. Yeah, I'll show that again in some tropical cyclone data. Okay, so what might actually be going on in the tropical cyclone record? Are we seeing a change in the mean or a change in the variability? Well, you're probably familiar with this kind of plot. This is the time series of annual numbers of tropical cyclones in the North Atlantic. In the purple is all tropical cyclones, and in the orange is the major hurricanes, the Cat 3 plus events. So you can see there's a lot of variability, and it's been increasing. That's the dashed line is the 20-year mean. But you also notice there's these bigger swings in more recent years, these very active years and a quiet year there. And we can quantify that by looking at the change in the standard deviation of the annual numbers of tropical cyclones through time. So the way I did this was to run a 20-year running window through that time series you just saw and looked at the standard deviation within that 20-year running window, and then plotted it in the solid line here. So you can see that the standard deviation has about doubled over the past 55 years. And I've just plotted that linear fit through it. So the variability of annual TC count has increased. And I'm not the first person to show this. I've basically adapted it from a paper that came out last year by some NOAA colleagues, this Lopez paper. And so this speaks to your question, Chris. I like to look at distributions of data to figure out or piece together what's going on. So I split the historical record in half. So the older period in the light pink and the more recent period in the darker pink. And so you can see there's been a shift to the right in the distribution, as we just saw in the time series. But not only that, if we remove the shift to the right, so now I've taken away the mean, so now the distributions are now both centered on 0. You can see the future distribution is wider at both tails. So there's been a contribution to the increase in the very active years from the shift to the right in the mean and this broadening of the variability. So both they've reinforced each other to increase the high years, but they've opposed each other at the low years, and the shift in the mean outweighs the shift in the variability. So again, this kind of result was demonstrated in Lopez. So what might be going on here? Well, let's look at sea surface temperatures over the main development region. And so that is the tropical North Atlantic, basically everything apart from the Caribbean. So here's a 55-year time series of summer average SST according to ERA5. So we have this warming. So we have warming and we have increasing tropical cyclone variability. So, if we put them together, we can see, so on the y-axis here is the variability in terms of the standard deviation of the annual numbers of tropical cyclones versus mean SST. And again, these are based on 20-year running means, so I'm really squeezing what we can get out of the data here. But we can see this is a log scale, so it's a log linear increase in variability. So this is interesting. Why might we be getting increased variability with warming? Well, there was this really nice paper that came out by Daniel Swain and colleagues a few months ago that pointed out that a lot of the behavior we see in hazards in the world could be connected to basically the Clausius-Clapeyron relationship, which I'll come on to in a moment. And basically the thesis in this review paper was that thermodynamics dominate the behavior, but then dynamics modulate it, either reinforcing or opposing the thermodynamic forcing for the change. So just as a quick reminder, the Clausius-Clapeyron relationship describes the change in vapor pressure with warming, and it rises exponentially by this rate here, about 7% per degree Celsius. So we're going to explore the scaling we saw in the variability versus warming with this Clausius-Clapeyron relationship. And sure enough, these lines here are now the 7% scaling lines. It's a log scale on the y. That's why you've got linear lines. And it was remarkable how close the scaling is. So this was curious. So why should this be? Why should variability be related to the increase or scale with the rise in vapor pressure with warming? So there's a few hypotheses here as to why that might be. So the first one is we know that hurricanes get their fuel from the ocean, and really they get them from the difference in moist static energy from the temperature of the surface of the ocean and the free atmosphere. And so I showed in an earlier paper that this disequilibrium rises at the same rate as the vapor pressure because there's a moisture term in the static energy equation. So the hypothesis is that storms that are already in favorable environments would intensify because of this increasing disequilibrium. However, at the same time, the flip side of the Clausius-Clapeyron relationship, in an atmosphere that's not saturated, it becomes increasingly thirsty. So the moisture deficit increases with warming. So this is like a curiosity of the Clausius-Clapeyron relationship, that even though the atmosphere is holding more water vapor with warming, it's also becoming further from its saturation value. And this was recognized in the Swain et al. Paper. And so the hypothesis is here that maybe weaker storms are going to be more susceptible to this rising moisture deficit. They're basically ventilated away. So if you look at that ventilation index from Brian Tang, that also, I believe, scales with Clausius-Clapeyron. So I think there's like a favoring of the more intense and a disfavoring of the weaker storms. That's the hypothesis. And I think that is indeed what we see in the behavior of tropical cyclone intensity. So this is the old rich get richer hypothesis. We've known this for a while. I'm just showing it in tropical cyclones. So here we've got tropical cyclone intensity along the bottom, and their sensitivity to warming, the rate of intensification per degree Kelvin along the y-axis. And anything to the right of here is hurricane strength, and anything to the left is more like tropical storms, tropical depressions. So only the strongest hurricanes have a significant response to, well, they have the greatest response to warming. And so you can, if this is the case, then the other side of this coin is that the variability should also increase between the intensity of the weaker storms and the strongest storms. So I think that's the connection then between the rich get richer behavior and this rising variability. But it's actually more interesting than that. So not only is the SST warming, but the SST itself is becoming more variable. So here's the North Atlantic SST standard deviation. So again, it's the 20-year running standard deviation. And that too has about doubled over the past 55 years. So there's bigger swings between cool waters and warm waters over the MDR. So this could maybe then be a circulation effect, if to the extent the SST patterns are related to changes in atmospheric circulation. That is reinforcing the thermodynamically forced hypothesis. But it's actually more even interesting than that. So we've got rising SST, we've got rising SSTs, we've got increasing SST variability, but also the tropical cyclones, the local environments to tropical cyclones are warming faster than the tropical mean. So that's what I showed here in a paper a few years ago. These are the vertical temperature profile trends for the tropical mean in orange versus, we'll just look at the blue one, local environments to hurricanes in the blue. And the dots here are the SSTs. So the trend in the local hurricane environment, the blue dot, is almost double the trend for the tropical mean. So this is curious. Does it mean that the warmest SSTs are warming the fastest? Or does it mean that the hurricanes are more preferentially selecting the warmest waters with warming? So I haven't quite figured it out, but it's a lot more interesting than just what we think of like just tropical mean warming. So there's lots to discover there. So just check. Now, if there's any statisticians in the audience, you're probably horrified about my lack of independence between my data points, especially when I'm using 20-year means. So I really squeeze the historical record to get as much information as possible. But fortunately, we do have a large sample size alternative provided to us by the Community Earth System Model High Resolution Ensemble. And the nice thing about this is it also provides us a larger range of SSTs. So just briefly then, this was generated by version 1.3 of the model. 0.25 degree atmosphere, TC permitting. It's a 10-member ensemble from 1940 to 2100 under historical and RCP 8.5 forcing. So we're really hitting the system with a hammer here. And just to demonstrate that we do indeed get tropical cyclones, here is a 4-decade period of track density, so the units, number of tracks per grid box in observations according to IB tracks, and a single CESM member. So we can argue, there's some spatial error, but we get tropical cyclones in the North Atlantic. So let's see what the environment is doing in this larger data set. So again, we get a much broader range of SST. Each single line here is an ensemble member. So 10 of them from 1920 to 2100. The box here is the historical period that I've blown up on the figure on the right. So we get the nice rise in SST, much like the observations, as we would hope. Again, each line is a single member. But I'm not seeing much evidence for that increase in variability of the SST across this historical period. So we got warming, we've probably got not much change in variance. And I'm showing that not much change in variance here. So this is within the historical period, the change in the variability of SST in the blue dashed lines, each member of the CESM, these are the linear fits. to that change in variance. And then the blue dashed line is what's happening in the observations. So it's quite clear the observations lie outside of the range of the CESM ensemble. And we could talk for a while about why that might be, but it's clear the CESM world is behaving differently to the observations in this metric. So how are the TCs responding in CESM? Well, here's the time series over that 180-year period of a gradual march downwards of the annual numbers of tropical cyclones. So the individual thin lines are annual data, the thick lines are the 20-year means, one line per member, and then the orange lines are the most intense storms. And I had to bias correct the intensity of storms from CESM, and I can talk about that if anyone's interested. But it's curious how the overall numbers go down, but the numbers of the most intense storms is flat. So as a result, obviously, on the right here, I'm showing there's a rise in the fraction of storms that exceed this major hurricane bias-corrected threshold going into the future. So we had the warming ocean just like the observations, but the TCs are behaving very differently in CESM world. So going back to these distribution plots, which I think is quite instructive. So I split up that 180-year period into 4 45-year periods, going from older periods in orange to future periods in purple. So we can see that gradual march backwards or to lower mean annual storm counts in the top figure. And then again, I put them all on top of each other, so I removed the difference in the mean, and the variability is about the same. So what might be going on here? So in CESM, there's no real change in the variability of storms. And this is an opposite result to a couple of recent papers, the Lopez paper and a Senna et al., who used different data sets to actually show an increase in TC variability in the future. So what might be going on here? So what I think is we'll notice that the variability is about the same, even though the mean is going down. And so the relative variability is actually increasing. So if I was to plot the coefficient of variability of storms, it would be increasing into the future. So I think there's still a forcing for increased variability from the warming North Atlantic, but whatever it is that's driving the mean to the left is the overwhelming that signature of the forcing for increased variability. So obviously I haven't shown that. That's just a hypothesis, and there's various experiments I want to try and piece apart what might be going on in CESM world and reconcile it with the observations. Okay. So I'll leave that there. As I say, it was exploratory work done in the past couple of weeks or so. But now I want to pull in some of my older work and work of others that I'll do very quickly, just a few slides here, to further explain collective behavior beyond tropical cyclones and how it relates to tropical cyclone behavior we've just seen. So the Swain et al. Review paper recognized the ubiquity of this CC scaling across hazards, and I'm providing some support that also in my work. So this is a project led by Derica Carroll Smith in M-Cubed, along with myself, QBE, Joanna Aldridge, and Andy Prine, who's now at ETH, where we also show rising variability in large hail. So this increasing variability in the future seems to cut across hazards. So here we developed some machine learning model for annual days of large hail. It's basically a large-scale predictors of large hail incidents, and here it is applied to ERA 5. So the region with the highest hail risk, of course, we're familiar with this, is also the region in the northern plains that's becoming more variable in the future. So this, if it's becoming more variable, possibly that might outweigh in the way the mean changes. So QBE here, the supporting, who's funding the work, is very interested in this from a risk perspective. And then Julia Kukli's here from ASP, homed in M-Cubed, also found the rich get richer concept in rain rates from MCSs in the CONUS 404 data. So many of you are probably familiar with the CONUS 404 runs, 40 years WRF simulation in historical, and a parallel run for under future conditions. So here she's showing that the future change in rain rate is a function of rain rate itself. So again, rich get richer in rain rates. And people have shown this in tropical cyclones also. So it's universal across the weather phenomena. And I really like this study that I contributed to that showed the rich get richer also extends to flood. So this study was led by Manuela Brunner when she was here in RAL. So here we're showing the relative future change in precipitation as a function of rarity or intensity. So the biggest change for the biggest events, and then discharge can be thought of as a measure of flood. So that also increases as a measure of the flood magnitude. And in fact, it even flips signs. So it's interesting that increases in only the heaviest precipitation leads to increases in flood. So that was a really nice piece of work. But again, it's evidence of this universal behavior. So again, let's just review the evidence. So yeah, this review paper recognized that this rich get richer appears across many different dimensions. So across hazards, hazard metrics, timescales, spatial scales, global regions, and I've shown that also in my work. And the other side of, or a consequence of that, the stretching of the range is increased variability, which can lead to a risk management challenge, especially if a lot of focus in the scientific and risk management world has been on changes in means. So I think this is an area rich in physical science questions about, how does thermodynamics drive this behavior as a function of intensity? And then it's an area ripe for integrated work to understand the implications of this and the connection with risk management. And I think it's also responsive to that key question I started with, how bad can the weather get this year? So we're gradually getting closer. All right, well, in the last few minutes, I just have 3 or 4 slides looking ahead as to the future role of NCAR. I think a vision as a driving force for science, the fundamental advances in science that are also used in risk management. So I'm returning to this slide. Remember, this is the opportunity space as I see it. It's advancing understanding of the Earth system in partnership with risk management with 2-way benefits. We can understand it. It provides us new lenses onto our science, and then the risk managers better understand their losses. So it's my opinion that we should be delivering less about data and more about fundamental understanding. So let me explain why I think that. Well, firstly, it's not climate services. We're not doing climate services here in NCAR. It's telling process-based stories about the hazards we see in the world. And so we're interested in fundamental insights about the underlying system. We're not interested in just explaining what we've experienced in the real world to date, because that's just a single realization of the system, nor are we interested in just explaining model world realizations, because again, as I mentioned before, next year is going to sample from that system that we aim to understand. It's not sampling from the observations or any modeled world. So the nice thing about fundamental understanding is it transcends any model or data set, because these risk managers don't know which model to use, they don't know which data set to pick up, and data sets have very short shelf lives. So we want something that transcends all that, that's enduring. And I think it helps with equity issues as well, because it fills in regions of the world that have a lack of data, if we can have this process-based understanding. And I've been told by risk managers that insights are a lot more broadly applicable than data sets. So, everyone loves a good data set, but something that's less tuned to a specific decision is a lot more broadly applicable, and it's also scalable. So, there's a lot of work that we do, in partnership that I just showed that I do with various companies but there's a finite number of NCAR staff. We can't solve everyone's problems. So if we offer these broadly applicable information, then it's scalable to solve a lot of problems. So the vision here is that NCAR leads and facilitates the community in providing the scientific foundations for effective risk management. So we know NCAR is a place to debate the scientific foundation, so I think it can be here also. It can also be a place to coordinate these partnerships. So I've had a lot of university people come to me asking, for advice on how to start up these kind of partnerships. And we're also very good at facilitating model and data set development. So that asterisk there is to remind me, I've just said we want understanding, not data, but a role for NCAR perhaps is creating data sets that enables community investigations to produce the insights. So I have some thoughts about what these models and data sets might look like, but I can explain that later. And then ultimately provide that open data that was a key recommendation from those president's reports. Okay, so hopefully I've piqued some of your interest. So how might you get involved if you're interested in working more on this? Well, as a first step then, I'd invite you to help me design a workshop. So we heard in the interviews, they wanted a space to just talk it out, kind of slightly unstructured and just get to the bottom of the root cause of the problems. And so the workshop then would be a place for like NCAR labs, university people and risk managers to come together and just hear each other's perspectives, understand and integrate them. So it's really about expanding our view of the challenge. And it would help us identify main gaps in perspective, knowledge, and theory. Because, for example, we don't have a theory of hazards in the global dynamical context, for example. So I think this is a key science driver also. And I think an important outcome would be to identify the role of NCAR again. What can it do to lift everyone up, to accelerate and fuel research in this area? Okay, well, I've come to the end. Thanks for listening. So rather than giving some key takeaways, you've just sat through 45 minutes of it, I wanted to finish with some personal reflections. So firstly, my partnerships with the private sector has really been career defining. And I'm grateful for that, because as we all know, as scientists, it's important to have a niche, what are you known for? And then people come to you. And I've been fortunate to have this collaboration and develop a reputation. I also recognize that I've benefited enormously from the collaborative spirit of NCAR. So it's always amazing to me how, someone can work on something for 12 months and then just email it to me and I can use it. So that's fantastic. I really appreciate that. And then finally, after learning a lot more about it over the past 20 years, I'm still in awe of the weather. But actually, I'm more in awe of the fact we can even model it. As Morris pointed out last week, the Wolf model gets it right every time. But also, and now we're transitioning into a world where we're also making the models usable. So I think that's something we can all be proud of there. So I'll leave it there. Thank you.
That was a great presentation, Jane. When you talk about variability, though, from my perspective, it seems like beyond the Clausius-Clapeyron equation, that the details of weather are related to the large-scale patterns. For example, we had a stationary upper-level trough for 7 days that produced this sequence of severe weather across the country. And it seems like, wouldn't you think that we need to look more at the variability of the larger scale patterns associated with variability?
No, that's a great point. So so that 7-day weather episode I started with was, these nice troughs that we all know coming over the springtime plains. But I think it's also a question of scale as well. Like on a weekly, 2-week, 4-week period, large scale variability is hugely defining. But on longer time scales, perhaps the role of thermodynamics rises as in importance. But
it could be the thermodynamics, the mean thermodynamics also tells us something about the large-scale weather patterns.
Well, well, they're not entirely independent, and there's a lot of work going on to connect the two. Yeah, no, exactly.
Yeah, but it seems like that needs to be considered somehow, the weather pattern part of this, because I mean we're wondering, even here in Colorado, the weather pattern seems to have changed dramatically in the 10, 20 years.
Yeah.
You know, in this year, for example, we had all these cutoff circulations, and that produces a very different environment for hazardous weather, independent of the thermodynamics. But of course, you know, you can't deny the role of thermodynamics as well. But
well, that's interesting. Now you're making me reframe it a little bit towards more forced changes and then unforced changes. So there could be forced circulation changes, as you just described, as well as thermodynamic, and then there's variability also on both sides. Yeah, okay. I like it.
All right, other questions?
So as you alluded to with the tropical cyclone record, the observational record is relatively short, and also like it has all sorts of issues depending on which record you use. Like if it's forecaster based, then there's all sorts of biases. If it's satellite based, then technology has changed. And then even the high resolution climate simulations don't quite tropical cyclones right. So how much confidence do we really have on what's happening with tropical cyclones and what might be happening into the future?
Yes. So there's multiple versions of the historical record. People have done a lot of work, tried to homogenize them. There's Jim Cosson's satellite-based intensity record that I've also explored. And I really wanted to just cut it off in about 1980 because it starts to get questionable before 1980. But I needed 10 more years to show some trends. The nice thing about CESM with all its biases that's common to all models is it's an almost entirely independent view of the world. So I think there's value in combining. But I think we can be a lot more creative than just passively using observations and passively downscaling GCMs. I think we can innovate how we combine observations and models. So more moving towards a research area where we're physically modeling the observations, but only using the physical processes that we need, rather than full-blown simulate everything in the whole climate system. So I think we can be a bit more creative of how we do that. So I think there's hope. Yeah.
Okay, thank you.
All right, thanks, James. Really nice talk. I was thinking back to the wonderful insights about the insurance and the reinsurance companies. And one thing I was wondering that you didn't explicitly touch on, do they have an explicit interest in compounding events in a given year, whether it's back-to-back TCs or TCs followed by heat or flooding? Since I would imagine that would really affect that vulnerability parameter. And did they talk about that and the need to predict it better?
Yeah, great question. So these catastrophe models, they assume every event is independent of all the other events. So there's one of the key missing dimensions then is dependency, either across the same type of hazard or across hazards. All the 4 dimensions of compoundedness is missing for the most part in catastrophe models, and they're well aware of that. And that's one of the reasons they look to us and university researchers to explore how they might be vulnerable to something they don't see in all their risk transfer decision making. So yeah, anything we can provide that is not already included in their CAT models they're very interested in, and that is dependencies, ranges, process-based understanding to give them confidence. Yeah, so there's a lot of opportunity.
All right, I'm going to go to a couple questions online. So first of all, from Andy Newman, great seminar, James. Place or use-based science has always historically struggled with scalability. Do you have any more thoughts on scalability of our science in terms of usefulness across sectors and applications, and how we could build coherent science programs at NCAR. So just a quick small question from Andy.
So I talked a lot today about the insurance sector, and that's because I'm most familiar, and they're very sophisticated users of our science, and a lot of them are ex-PhDs, and some are even ex-NCAR staff. So that's been an easy entry point. But in terms of building something or scaling it across different sectors, I'm going to come back to these fundamental insights, and it's not just discovering these insights, it's communicating them as well. So even when I think I'm doing a great job at communicating to a non-scientific audience, I'm regularly told it's not working. So there are ways in telling stories to connect across sectors that have not as much expertise, and basically they have 10 minutes to listen to you and make a decision. So I think it's part advancing fundamental insight, and it's part being a lot better at communication to scale what we do. Yeah.
All right, and I'm going to take the last question from online from Dave Lawrence. I found your comment interesting about how stakeholders want to know about our fundamental understanding advances. When I am involved in these conversations, it seems like the request is for directly relevant model output or diagnostics. How would you reconcile this discrepancy in experience?
Okay. So I always ask this question, don't you just want the data? Why do you want to know the story behind what you're seeing in the data? And I think it's a question of trust in the people I talk to anyway. They need to trust the data or the information they extract from the data. And trust comes from understanding, and so they look to scientists to tell them they know why the data looks the way it does. So that's been my experience almost universally. In the partnerships I haven't had the experience where people just want the data passively, because the regulators then ask the industry, do you understand the information you've used to make your decisions? And if they don't, then they're not allowed to, or less allowed to do business. So.
All right, thanks everyone for your questions, and thank you again for a terrific talk, Jay.